So let's see. Let's look at this one. How do you find some spin in the theta direction to be, or let's say in the n direction, +1? Yes? Come in. So how do you find this state?
You put a detector that is
Yeah, okay, so in the detector there will be the cosine dependence, but now theoretically we have to understand why it is the cosine, right? So that's the question. So the thing will be, initially you have something in the z direction, right? You put the Stern-Gerlach experiment in the z direction, so let's say you have this plus z state. So then you put another Stern-Gerlach experiment in the n direction, then the amplitudes will be as n hat is equal to plus or minus 1. So these will be how they will be split, or in fact, it's absolute squares. So you have to determine this one. What is this? So you have to first determine this one. Now, how do you determine this one?
what are we determining exactly?
I mean, we always talk about the spin in the z direction being plus or minus 1, or the x direction being plus or minus 1. But they are kind of arbitrary directions. So let's say that you first choose your x, y, z axis. They are fixed. Then the question is, what is a state that has a spin plus 1 in an arbitrary n direction? What is that state?
Spherical bir şey olmaz mı?
Now we have to write down the states in terms of plus z and minus z states. So this state,
We should define it in the base.
this will be a plus z plus b minus z,
And then you multiply with
a squared plus b squared would be 1. And so the answer to your question is this one. Yes, and let's say this a plus b a minus. So your a plus a minus squared, their sum is 0, Sn is equal to plus or minus 1. This will be a plus or minus. And with some plus or minus sign. They will turn out to be cosine and sine of, not theta by the way. If I'm not wrong, it should be theta over 2. Or, I don't know, I don't remember the answer, but you have to work it out. It should be a cosine because it should, I mean, if you define the theta as the angle with, that n makes with the z, it should go to 0. Well, it should go to 1 when theta is equal to 0. So that's the cosine. But you have to just work it out.
Thank you.
Any other questions about perturbation theory this time? Okay. So there's just one more topic in perturbation theory which we should cover. If you remember on Sunday's lecture, we were discussing this hyperfine splitting. The idea is, we said that, okay, the electron is revolving around the proton, and hence it feels in the rest frame of the electron, we said that, okay, the proton is moving, and hence it creates a magnetic field that the spin of the electron feels. So that's how we come to the conclusion that there should be this hyperfine splitting. But the proton also has a magnetic dipole moment. And just like any magnetic dipole, the proton creates a magnetic field not due to its motion, but also due to its spin. And the magnetic dipole moment of the proton is the gyromagnetic ratio of the proton times the charge of the proton, which is just E, divided by twice the mass of the proton in the spin direction. And we had already seen that the magnetic dipole moment of the electron, well, the gyromagnetic ratio for the electron, which is very close to 2. Charge of the electron, which is minus E divided by 2, and proton in the spin of the electron. Now the proton has this magnetic dipole moment, so it creates a magnetic field. And the magnetic field created by a dipole, okay, let me just look it up. Okay, we have this usual mu 0 over 4 pi, it's 1 over r cubed, 3 mu dot r hat minus mu. This is for any magnetic dipole, plus 2 mu 0 over 3 mu Dirac delta r. Which one? Now, this is for any magnetic dipole. In our case, it will be mu p. This is the expression of... Hmm? No, me. You're right. This is the mass of the electron. Now, if you do this derivation, in most of the time in classical electrodynamics, we don't see the last term because we always look at the magnetic field at a faraway distance. But that term also exists, and the main source is that the Laplacian of 1 over r is proportional to the Dirac delta of r. So if you are careful, you will see that there is also that term over there. So we now have the h prime for the electron. It will be minus the magnetic dipole moment of the electron times the magnetic field created by the proton, which is minus mu 0 over 4 pi 1 over r cubed 3 mu proton dot r hat mu electron dot r hat minus mu proton dot mu electron plus 2 mu 0 over 3 mu proton dot mu electron. And mu is nothing but proportional to the spin of the particles. So if you just put the proportionality constants, etc., what you get is this is equal to mu 0 over 4 pi 1 over r cubed gp 1 over 2 m proton times m electron. I just use the gyromagnetic ratio of the electron to be 2 e squared 3 spin of the proton, spin of the electron, minus sp dot se, plus or minus 2 mu 0 over 3 gp e squared over 2mp me, spin of the proton, spin of the electron. Now, this is called the tensor interaction. Did you hear the word tensor before? And this is called the scalar, spin-spin. Interaction. Now, of course, here we have the Dirac delta. Yes. No, there's no vector sign. So we have the Dirac delta x times Dirac delta y times Dirac delta z. It's a product of 3 Dirac deltas. Now, both of them you can write in terms of the total spin of the system, the electron plus the proton system. In the case of sp dot se, this you can write as 1 over 2 spin of the proton plus the spin of the electron minus the spin of the proton squared minus the spin of the electron squared for both of the terms in the second line and in the first line. And you can do a similar thing for sp dot r hat. This is 1 over 2 sp plus se. Now this is squared sp dot r hat plus se dot r hat squared minus sp dot r hat squared minus se dot r hat squared. So basically, both. What is this one, by the way? SE dot r hat squared. Okay, this is equal to h bar squared times. What is sp dot r hat? Se dot r hat. Along the r direction. So what are the possible values? No, there's no zero. For the electron, it's either plus 1/2 plus h bar over 2 or minus h bar over 2. So those are the two possible values of Se dot r hat, the eigenvalues. Well, the square of both of them is h bar squared over 4. So Se dot r hat squared, acting on my states with a single electron, is always h bar squared over 4. And similarly for Sp dot r hat, the proton also is a spin 1/2 particle. So along any direction, its spin can be either plus h bar over 2 or minus h bar over 2. In both cases, the square is equal to h bar squared over 4. And these operators, and okay, Se squared is equal to Sp squared, and these are all equal to 3 h bar squared over 4. And the total, so these operators appearing over here is a function of the total spin, not of the spin of the electron or the spin of the proton separately. Now, if we want to diagonalize our H prime, we have a degenerate perturbation theory, we have to diagonalize our states. So now our states, okay, initially without considering the spin, we had these states. Then we added the spin of the electron, Se, Ms, E. And now we add the spin of the proton, S proton, Ms proton. These are a possible set of basis states. Now this interaction over here, these interactions, all of them, tells me that rather than using the basis in which the electron and the proton have definite spins, we should switch to a state in which electron and proton have a total spin. So rather than these states, we should go to NLM, spin of the electron, spin of the proton. Well, these are both 1/2. We could have just ignored them. And S total, let's say Ms. And S total can be 0 or 1. And Ms is from minus S total up to plus S total. Now, if the total spin is 0, we call this the singlet state. And if S total is equal to 1, well, Ms can take 3 different values, minus 1, 0, and 1. So that's why we called it the triplet state. Well, these are just the names. If the total spin is 0, then there's a single such state. That's why we call it the singlet state. And if the total spin is 1, we call it the triplet state. There's no half. I mean, we have an electron and a proton. Doublets. They form doublets. Sure. Now, in this case, there's implicitly the assumption that L is equal to 0. So since L is equal to 0, the total spin also will specify the sum of the spins of the electron and the proton of the hydrogen also gives me the total angular momentum of the hydrogen itself, since L is equal to 0. Now, it makes calculation easier. Well, you will see in your, it will be an exercise for you to calculate the matrix element of this one for, let's say, L is equal to 1, the possible matrix elements. For L is equal to 0, it is kind of easy because it's E dot R hat, SP dot R hat times 3 minus SE dot SP. If you take the matrix element between L is equal to 0 states, this is 0. So at least if we are studying the effect of this spin-spin coupling on the L equal to 0 states, we don't need to worry about the angular moment. We don't need to worry about the tensor states. Now then the only thing left is this one. So the correction to the energy let's say n is equal to 0 will be 0, 0, 0 minus 2 mu 0 over 3 g proton E squared over 2 MP ME. So let's also add the ST. SP dot SE Dirac delta R. No. 0, 0, 0 ST state. This will be the correction. And this will be minus 2 mu 0 over 3. We got all these constants. And we have the wave function at origin squared. That is because of the Dirac delta. And the product of the spins will be 1 over 2 S total squared minus 3 over 2 H bar squared. Well, all these constants we know the wave function also. So you can just put in the numbers. You can see that okay, so we have this triplet state, we have this singlet state, their energies are now shifted from each other. You can look at the change in the energy, the difference in the energy of these states. This change, if you put in the numbers, is at this frequency.
Megahertz.
Megahertz.
Ah, okay.
Now this is my amp. Which is, by the way, is 21 centimeters, or these are the microwaves. So you have the microwave transitions. Well, this is delta E is of the order of 10 to the power minus 6 electron volts. Now, measuring delta E itself will be quite difficult. As we had discussed, even the thermal motion will just, it will be hard to difficult, but nevertheless we can measure the difference, because given a single hydrogen atom, the energy level is fixed. The thermal motion is just an average of many hydrogen atoms. So on the average they will be lost, the absolute value of the energy, but the shifts is still measurable, although it's very small. Why is it so small compared to the other perturbations? By the way, this is the reason why it's called the hyperfine, is that it is so small. It's much smaller. The other ones, if you remember, they're of the order of 10 to the power minus 4 electron volts.
And the relativistic was 10 to minus 2.
No, it should be 10 to the power minus 4. Now, the correction, the relative correction was 10 to the power minus 5. The energy levels are of the order of 10 electron volts, so the correction is 10 to the power minus 4 electron volts. At least for the ground state, it's of the order of 10 to the power minus 4 electron volts. Why is this one much smaller? Do you have a guess? Yeah, I mean, why is it small? I mean, the other ones were small because the corrections was of the order of E over the mc squared, so that we could understand why it should be 10 to the power minus 5, the fractional change. Yep. This time in the relativistic correction we have the mass of the electron. Now we have the mass of the proton here also. And mass of the proton is like 10 to the power 3 times more than the mass of the electron. So I'm kind of surprised that it only makes a change. No, it makes a change of the order of 10 to the power minus 2. Any questions? Okay. Well, let's look at one more perturbative effect, and then kind of that will be the end of our time-independent perturbation theory discussions. So let's look at the Stark effect. Now we put the hydrogen atom in a magnetic field, and that kind of gave us the Zeeman effect. And now we put the hydrogen atom in an electric field. So let's assume we put it in a uniform electric field, external that's uniform in the z direction. Let's just choose the z direction as the direction of our electric field. So what is the corresponding potential energy for the electron? For a uniform electric field, what is the potential energy? 1 over 4 pi E0 times E squared over R squared. The potential is R. So is this a uniform potential? Does this correspond to a uniform electric field?
Electric field uncharged due to another charge.
Yeah, I mean, the question is, we have a uniform electric field, and remember this one. So E external is uniform. So what is the potential energy? Come on, you have already forgotten all your other courses? You see, let's look at this one. The derivative should be constant and only in the z direction. So it should be, yes, H prime is equal to the charge minus E times the external field times minus Z. So this is my potential, V. If you take its gradient, it just gives you a constant Ex. Okay, so, well, because in the definition of the electric field, there is a minus one. Yeah. So we know our perturbation Hamiltonian. Ex Z. Now let's calculate the corrections. M, L, M, H prime, and L, M. What can you say about this one? Z or X or Y, whichever one you like.
Do the same operation.
So it's 0. Now the easiest way for me to see this one is using the parity. Remember what we discussed, the parity. Now the nice thing about the parity is the spherical harmonics, when you apply the parity to them, they get -1 to the L, YLM. They are eigenstates of the parity. So parity acting on Z and LM, under parity Z becomes -Z, and LM state becomes -1 to the power L plus 1, and LM, no sorry, not 1. Let me finish and then you can ask. And LM, so this is equal to -1 to the L plus 1 Z and LM. So Z and LM is a state, is an eigenstate of parity with an eigenvalue -1 to the L plus 1. Whereas this NLM is a state, eigenstate of parity with an eigenvalue -1 to the L. And hence these two states are eigenstates of parity with different eigenvalues, and hence they have to be orthogonal to each other. And NLM, L prime, M prime, parity, and LM, it is non-zero only if L prime minus L is odd. Now, in fact, we will see that it should be 1, plus or minus 1. Only in that case, it's non-zero. Yes, your question.
Bu dediğiniz şey nereden nereye?
Well, in the hydrogen atom, we choose the origin to be the position of the proton or the position of the center of mass. And the direction is just whichever one you like. You just choose an arbitrary direction. In this case, we choose the z-axis to be in the direction of the electric field. So that is z. From the position of the proton along the direction of the electric field.
Elektron için mi yazdık? Elektron için mi? Proton sabit kaldığını mı düşünüyorsun?
Yes. I mean, you can either say that we are only looking at the electron, the proton is infinitely heavy, or you can just move from the two-body problem to the equivalent one-body problem, which is the electron basically with the reduced mass. So it seems that there is no perturbation. If this is 0, oops, sorry, this is not P, this is Z. So if this is 0, well, this matrix element is 0, there doesn't seem to be any perturbation at first order. I mean, there's no correction at first order. Do you agree? Yes? Okay, so to the energies, there is no first order correction. Agree? Yes? Yes, I am missing 2 knots. Do you agree?
Ben de evet yok hocam. Ben kalıyorum.
Okay, do you agree? No, I forgot your name. Do you agree?
Yes,
You are all wrong. Remember, we are doing degenerate perturbation theory. So in the degenerate perturbation theory, we have to make sure that the perturbation we are adding does not mix states. Its matrix element between different degenerate states should be 0. Let's look at this expression over here. If n is the same in both states, then they are degenerate, right? Because the energy depends only on n and not on L if we ignore all other effects. But we have seen that if L and L prime differ by 1, then the matrix element is non-zero. But then the Hamiltonian has non-zero matrix element between degenerate states. So we cannot use degenerate perturbation, non-degenerate perturbation theory. So we have to first write down a good basis, which this one is. NLM states are not a good basis. Now, of course, it is a degenerate perturbation theory if n is non-zero. If n is 0, there is no correction. To the energies. Because if n is 0, then there's just a single state. Well, n is 1, sorry. The only possible value of L is 0, and there's no degenerate state. Now the problem becomes when n is equal to 2. So if n is equal to 2, then 2, 0, 0, 2, 1, 1, 2, 1, 0, 2, 1, minus 1, they are degenerate. And some of their matrix elements will be non-zero. No, n is, sorry, yes. So let's see. 2, 0, 0, z, 2, 0, 0. We already said that this is 0. Two zero zero z 2 1 1. What can you say about this? Is it or not?
And the first one.
Okay, true. What about the M? Let's see, what is LZ commutator with Z? So that is, just imagine you have something in the Z direction, you rotate around the Z, so that thing changes or not? It doesn't change. So LZ is kind of, it rotates your system around the Z axis. But if you rotate your system around the Z axis, none of the Z coordinates change. So LZ and Z, they commute. I mean, you can also say that LZ depends on Px, Py, X, and Y. It doesn't depend on Pz. So the commutator will be 0. But if that is the case, let's just consider this matrix element. 2, 0, 0, LZ, Z, 2, 1, 1. This will be equal to 2, 0, 0. This should be 0 to start with, because the commutator is 0. If we write the commutator explicitly, LZ, Z minus Z, LZ, 2, 1, 1. Well, LZ acting to the left just gives me 0, because M is 0. So this is equal to minus H bar, 2, 0, 0, Z, 2, 1, 1. And hence this matrix element should be 0. I mean, you can also say that since our electric field is in the Z direction, rotations around the Z axis is still our symmetry. So MZ is a good quantum number. Our Hamiltonian doesn't mix states with the same MZ, with different MZ, sorry. MZ is the angular momentum in the Z direction commutes, is conserved. So in fact, in that case, the only non-zero off-diagonal matrix element is this one, 2, 0, 0, Z, 2, 1, 0. This is the only non-zero matrix element. This is not 0. So if you would write the H prime matrix, it will be, let's say, this is L is equal to 0. This is, or let's say, 0, 0. 1 minus 1 1, 1 minus 1, no, 1 0, and 1 minus 1, and similar ordering for the rows, we will have 0 0 matrix element will be the diagonals will be non-zero. And among the off diagonals, the only one that won't be zero will be this one and this one. All the other ones will be zeros. Yes.
Did we change the basis now?
Not yet.
Not yet.
Not yet. This is our H prime matrix.
What are the diagonal terms not?
Oh, sorry, you are right. Diagonal matrix elements are zero. These are the zero. And let's just say that those matrix elements are, let's just call them delta. So delta is equal to H prime 2 1 0 2 0 0. What are the corresponding eigenvalues? Well, let's see. We have the 2 0 0. No, 2 1 1 is already an eigenvector. 2 0 2 1 minus 1 is an eigenvector. Now, if you calculated the other eigenvalues, you will see that they are 1 over square root of 2, 2 1 0 plus 2 0 0, and 1 over square root of 2, 2 1 0 minus 2 0 0. And the corresponding eigenvalues for 2 1 1, it will be it's already 0. These are the eigenvalues. For 2 1 minus 1, the corresponding eigenvalue is again 0. They are already eigenvectors if they correspond to this row and this row. The other ones will be delta and minus delta. So basically, we started with a degenerate state, and that split it into three parts. One was shifted up, the other one is shifted down, and the other one just stayed there. There's no correction to that. So you have to be a bit careful. Just because the diagonal matrix elements are 0 doesn't mean that there is no correction to your states if you are doing degenerate perturbation theory. Any last questions? Yes. I mean, of course, you are not yet done with perturbation. You will have homework on perturbation, but I'm kind of done. Now, the perturbation theory is nice if the perturbations are small. If there is some H0, which you can exactly solve, and the correction to H0 is small, then perturbation theory is great. For electromagnetic interactions, as I was mentioning last week, we can calculate certain quantities up to 20th decimal point, 24th digit after the decimal point, and they agree perfectly well with the experiment. But if you don't get a small perturbation, then what to do? So that we will be studying a few more alternative methods to get approximate solutions without using the perturbation theory in the next couple of weeks. So see you on Friday.